Hey, what's up? Alex here. Today we'll take a look on new LLM Claude 3.5 Sonnet. It was released 2 days ago. Let's take a look on scores. So Anthropic is proud about best possible numbers. Basically, this is state-of-the-art model as for today. And code is 92%, which is great. Much better than anything else on the market nowadays. So today I will do a quick test, my favorite test. I will ask LLM to write some code and try to see how it performs. Let's jump right into it. So let's start new conversation. And my perfect test, my favorite test is Demosaic raw image from Fujifilm X-Trans sensor. Basically, what this means. Raw images from digital cameras they are not color. Actually, sensors cannot sense color. Instead, they use something called color filter array, which filters out lights, and each individual pixel actually senses only one of the three main colors: red, green, and blue. X-Trans sensor has specific pattern, which is a piece of it is displayed currently on the page, on the screen. And it's very tricky to decode this using software algorithms and to decode it properly. There is no good, fast, open source algorithm available currently. So this task is tricky for LLM because it has no, at least I expect that it has no knowledge about this algorithm in its training dataset. So my task is check if LLM can actually write this code, which will do something meaningful with this task. Basically, to convert this array of colorful pixels into RGB, into proper color. Let's try. So I will put this prompt, basically write the best possible JavaScript code to the Demosaic raw image from Fujifilm sensor. Why JavaScript? Why not Python? Because in Python, I see LLM tries to use a lot of Python's built-in algorithms, libraries, etc., which are very great in mathematics, and this hides a lot of logic, which it's not easy to understand and read, at least for me. And for this purpose, I want to see some raw calculations, raw algorithm without hiding something under the libraries. And JavaScript code is perfectly fine for this task. And also, I will do one more step, which I did not try it previously. I will instruct it specifically make sure to handle all possible corner cases and Demosaic artifacts. Basically, I'm saying it, hey, I want to see like best possible algorithm. I don't want to see some mockup. I want to see final. Let's add some final. Provide final ready to use algorithm. Okay, let's take a look what will it generate for us. Okay, so it generates some code. It encodes CFA, it's color filter array abbreviation, and it's already failed right here because this is not correct pattern. Let's take a look on the image. Here we see that we have big squares, 2 by 2 pixels of green, and all other pixels are red, green, and blue. Here we don't have such green blocks 2 by 2 at all. So it's the first most obvious pitfall here. Let's take a look. So get pixel will output color. Okay, set pixel. Get color at position. Okay, it will decode raw image according to CFA pattern. Interpolate green. Okay, here's interpolation. It obviously that it will interpolate green somehow differently. Wise decision. Why wise? Because in X-trans sensors we have much more information in green colors, and if we'll take a look on specifically green channel here, we can see that like interpolation of green is very easy because each pixel surrounded by multiple other green colors. You can do some different tasks, different like approaches. You can interpolate vertically, you can sum everything around and do some average. You can do like feature detection and use these features to interpolate more accurately, etc. So obviously interpolation of green will be significantly different from interpolation, for example, of red, because for red we have a lot of missing information, and for this missing information we need to come up with some very clever and very tricky algorithms to make this precise and preserve details here. So okay, let's jump back to our code. So what will it do? For green, from what I see, it will do basically averaging. It will go 3 by 3 pixels and average, just do plain average. So it's not bad. Basically, what will it what it will do? It will go 1 second. It will, for example, for this pixel, it will select this, not this, like this region, and use this pixel, this, and this, and calculate average for this one. It will work. Like it's a good start. It's obvious start, but it's not perfect. Okay, let's move on. About why it's not perfect, I will talk later. Interpolate red and blue. Okay, it understands that for red and blue we need to interpolate differently. I just explained why. Okay, so it will do pretty the same. It will sum up, but it will get bigger window, like 2 by 2, not 2 by 2, like 5 by 5 pixels. Let's take a look. For example, red. So, for example, if it wants to interpolate this pixel, it will go with such square, calculate all reds inside it, and it will do very clever thing here. Basically, what it will do, it will use proximity. Why proximity? Color proximity. Let me illustrate you. So, color spectrum. Sensitivity. So, if we take a look on this chart, basically this is how human eye is sensitive to different colors. As you can see, we are mostly sensitive to like bluish green area, and this algorithms leverages from this. Basically, it sees if a nearby red color we have green, we can use green like as proximate color to get additional information. Basically, it extracts information from green channel and try to populate red channel with this additional information from green channel. Basically, it finds difference. In this spot, what is the delta between red and green? And it assumes that in like if here delta between red and green is like 10, for example, then probably here it also will be 10. So we can get the green color here or nearby and calculate red not only based on red colors here, but also on information from green channel. Very clever move. Nice approach. Really clever. And if we'll talk about this, I can also we have something called rods and cones, I believe. Human eye also is a very clever tool. Some cells in our eye sense like this. One cell can sense this area, another cell can sense this area, and third cell type of cells can short, medium, long. Basically, this length of our cone cells, and they are sensitive to different wavelengths. Human eye also can sense properly in all spectrum. It uses very clever algorithms inside our brain, and to properly distinguish between like green color, for example, because like two types of cell can sense it. We use difference. Actually, we subtract value from like of long cell cone from value of medium cell, and this is how we better understand and better distinguish the colors. And it's okay. It's another topic. Let's return to our like interpolate red blue algorithm. Okay, so this is quite clever, very clever approach, basically to use information from green color, apply it to these sums, and then round up. Okay, it will provide not bad results, but with some caveats. Also, then we have function to apply median filter. Middle value of I'm not sure why do we need it. I will take later. Okay, so what algorithm will it use? At first it will interpolate green channel. Okay, so it will interpolate green channel across the board. So as a result, what will we have? So after first step, we'll populate all green pixels here using this average algorithm with 3x3 segment. I'm not super happy about just averaging, but that's fine. So this will allow us to have green pixel in any pixel of our, basically green channel in all pixels of our image, and then this green channel will help us to better decode, deconstruct red and green channels. Okay, then we interpolate red and blue channels. And then they apply median filters for red channel to reduce artifacts. So basically, what is parameter here? It's just channel number. Okay. For blue channel, it's probably fine. For red channel, again, I'm not super happy because like human eye has very low sensitivity in blue channel. Just because you can see like from this image like only one type of cone cells has sensitivity here, like two other have much high sensitivity in red and greenish, bluish green, yellow or red areas. So I'm not super happy about this, but it's still okay. So basically just averaging, not averaging, like finding median values. Okay, just smoothing out. Okay, that's all. My general impression, like this algorithm basically won't work out of the box. So it's not working. Why not working? Like pattern is absolutely incorrect. It will decode garbage in, garbage out. It's obviously Algorithm itself is better than I would expect, because it was able to get to try to get information from green channels, but it will have a lot of problems in some corner cases. Let me explain. Let me explain with some example. So green. Let's take a look on blue channel. Not blue. Let's take a look on this image. When you have some features, let's say vertical lines or horizontal lines, which are very distinctive on the image, they can cause very hard times for this algorithm to work. Why? Because from sensor perspective, this looks like this. A lot of pixels, and we don't have much information on other areas. And this is very tricky to decode properly, because when you try to decode it, it will look like here. For example, let's imagine that you want to decode this pixel or this one, for example. If you want to decode green pixel here, it won't be black. It will be some kind of greenish. The same story like here. All these pixels, green pixel, will cause like contamination of these pixels as well. The same story for blue, for green, for red. Basically, this line, if it will be decoded with this algorithm, it will be anything but not white line. This is tricky task. Another example, like diagonal features, like when some lines are crossing this pattern diagonally, it also could be tricky, because if we will take a look how this line will be represented for X-trans sensor, it will be all green pixels. There is no information about red or blue. How you can guess that this line is white? Why it's not green? Why it's not any other color? Because we don't have any information about other colors whatsoever, only green pixels. How this algorithm can understand if it's what color it is? Basically, it's very tricky. It's corner case, right? But this algorithm is unable to understand this, and I would expect from Gen AGI that it eventually will be able to come up with these corner cases. I specifically instructed it, hey, please handle all possible corner cases. Okay, let's do a couple of more steps here. Let's try to fix like pattern at first. Here's correct CFA pattern for X-trans sensor. Oops, sorry. Stop. Okay. Okay, here's pattern. I hope you all understand. Okay, yeah, now it understands this pattern. Yeah. Okay, please update code and fix pattern. Correct one is and let's enumerate what we want to fix. B, we want to fix problems with thin vertical pix lines. Let's take a look how it will handle it. And C, let's see like 1 pix white diagonal lines. Okay, so we provided additional information, some suggestions, what we want to see. And let's take a look how it will handle it. Okay, pattern looks okay. Get pixel, set pixel. Get color at position. Interpolate green. Okay, now it's interesting because now it use some kind of feature detection matrix. How to use weights? Yeah, so basically it's looking for this feature, for this cross, and interpolates in a way that basically it will include information from nearby pixels. Interpolate red, blue. Okay, here it does pretty similar job. It uses some kind of feature amplification. It will amplify current pixel, will provide more values for vertical and horizontal ones, and pieces and smaller weights to diagonal. But since it uses 3x3 matrix, it won't work properly. I will show you why it won't work properly. Just because, so if we'll, let me hide this. So if we'll take a look on this image, and let's imagine that we want to use this pixel. And if we have vertical lines, so distance to next closest value, pixel where we have some value, is like more than 2 pixels. It's like 1, 2, 3, 4, 5 pixels in this dimension, in this direction, in vertical dimensions. The same story for horizontal interpolation. If we want to interpolate this pixel, it will work only on this. It will work only in this area, and it won't be able to see this pixel, especially if we have only like white line across, which is suboptimal in my opinion. So basically, to interpolate this pixel, we have only 2 pixels, and so it will give more weight to these pixels than this. It will use 2-to-1 ratio here. Basically, it will be, let's say, gradiental interpolation. Okay, not bad, but not perfect. Apply directional filter. Oh, this is interesting. I never saw this before. What will it do? Let's ask it. Hey, please comment all. Please provide comments for all functions and pieces of code. Let's ask LLM to explain what it does here, because I'm not sure. Values 3, values 5. 1, 2, 3, 4, 5. Okay. So it's extract basically from pixels this subset of like 3x3. Then it calculates difference. So it detects difference between left and right pixel, top, bottom, and diagonal pixels. Okay. It finds where the difference is minimal. And if mean difference. So basically what it does, I understand. It looks for all pixels nearby. And detects in which direction. Basically, I'm interested where it applies it. Yeah, so what it does, it looks in which direction there is a minimal difference, basically where gradient is the smoothest. How this works? Let's imagine that we have some like line here, like this line. Not line, like let's imagine that we have this is black. And this means, for example, if we want to interpolate this pixel, difference between this blue pixel and this pixel will be large, because here will be like 0, this will be, let's say, 100. Difference is huge. But if it will take a look between these pixels, this pixel and this pixel, this both pixels are 100. Difference is minimal. So it makes sense to smooth and do averaging, basically interpolation based on this direction, not on this, just because here delta is huge and here is very small. So it's very clever decision. Basically it detects in which direction we have the let's say most smooth gradient, and it interpolates in this direction. Nice move. I very like this decision. And actual demosaic. So it's first again, it interpolates green channel, interpolates red and blue. Keep in mind that it interpolates in short window where only actually 2 pixels of red and blue can from 2 to 3 pixels, because like window, let's take a look on window 3 by 3. So here like 3 pixels, 3 pixels, in this case like 1 pixel, but we don't need to interpolate it. Here we will have only 2 pixels, and in this case there will be very inefficient interpolation, I would say. So this algorithm is way not perfect, way too off. And then it applies filter to reduce artifacts. So it's not doing anymore. It's not doing median filter as it did in first example. Now it will apply filter. But what this filter actually does? It just smooths out. Basically, it finds after interpolation these gradients and just basically polish or like do small blur in less harmful directions. Yeah. Okay. Not bad, but not perfect. And let's take a look how it commented it. Let's double check that my understanding of... Oh, actually it's generated comments for documentation. Nice. But let's take a look on this apply directional filter. Get color, calculated column difference in each direction, right? Yeah. Choose the direction with the smallest difference. Average of 5 pixels. Okay. Okay, and let's do like final touch here. I will suggest that hey, for red and blue channels, it looks like for red and blue channels we have very few pixels, 3 by 3 interpolation window. Could you please handle this issue somehow better? And let's try ask it to do something like chain of thoughts, like please come up with a few ideas how to address this problem. Reflect on them and come up and implement the most the best one. Okay, so now we are not asking to generate like code out of the box. We'll ask to come up with a few ideas and reflect on them and basically then interpolate. Let's take a look. What ideas? Later interpolation window. Yeah, straightforward, not super efficient. Two-step interpolation. First interpolate at non-red blue positions and fill in the gaps. If positions are known, why do interpolate there? Basically, one of the best possible, let's say, open source external sensor interpolation algorithm is implemented in Darktable, and a few other open source tools. It's the same algorithm, and it uses 3 steps for interpolation, up to 3. You can configure, but like the best results are 3 steps, but it's super slow. I would like to avoid it. Okay, adaptive window size. Use different window sizes based on the locant pattern. Or much better idea. Green-based interpolation. Use already. Yeah, this already implemented. I don't know why it's trying to come up with this idea. Pattern-aware interpolation. Utilize the known X-trans pattern to selectively choose pixel for interpolation. I have no idea what this means in this context. Simple, by my blur fine details, makes sense. Two-step, more accurate by computationally intensive. Yes, true. Adaptive window, potentially most accurate but complex to implement. True. Green-based, leverages the dense green channel, good for maintaining image structure. Yes, but green and the blue, they are not super close. I'm not sure that it's work the best. And pattern aware, tailored to X-trans, potentially most accurate for this specific sensor. Maybe. Okay, I believe a combination of approaches 4 and 5 would yield the best results. Adaptive window and green-based. Yep, makes sense. Okay, what do we have here? Maximum distance 3. Again, 3 is very small. Again, let's take a look. Like, we need to have at least 5 because we need to reach to these pixels in some cases. Because like for lines, for some features, we would really want to interpolate from these pixels, like between these two, using some gradient. Like 3 is very small. I would adjust it. So what is happening here? We go in. Okay, so it's 3. It's -3. 1, 2, 3. Well, still small. I would say 5 at least. It checks if color this position is target color. Calculate Manhattan distance. Weight based on distance. Okay, 1 is added to avoid division by 0, I believe. Green diff. Yeah, so it's basically doing gradient. Do this. Where's the weight? Adjusted value, raw data. So I don't see significant difference. Like, I don't see anything like tailor it to. It's adaptive. Sorry. So adaptive window, yep. What is adaptive here? Where is adaptive? I don't see adaptive. Let's just search area, distance-based weighting. Yes, really good idea. Green guided interpolation, also a good idea. Pattern aware. It's bullshit. Fallback mechanism. If no target color pixel are found, which should be rare, it falls back to green value. Oh, I would avoid this. Okay, So that's fine, but again, for specifically this algorithm, it does nothing about like vertical lines, horizontal lines, diagonal lines. It just interpolate in these directions, and it will cause a lot of artifacts. Like image at first glance will look okay, but like fine details, it will be scattered. This is not perfect. Okay, so let's wrap up. So basically, at this point of time, a state-of-the-art model is not able to generate algorithm which will decode X-trans sensor. Right out of the box, it fails even to identify this pattern, color filter array, like it's incorrect. Provided algorithms are suboptimal, like they're pretty good. Like for first attempt, it's very, especially like guided by green channel, it's very clever decision. Very good idea to interpolate green at first. So probably it saw this code somewhere, I would assume. I don't see any, let's say, science that the LLM understands the problem. So it tries to guess, but it don't understand what I want to do. Let's ask LLM to reflect on this. Please reflect on your solution. How accurate Demosaic algorithm is. Scale from 0 to 10. What could be improved? And let's give it another chance. Please provide code with all your best ideas and improvements. So I specifically don't provide additional information. I just want to see if it will be able to reflect somehow. Okay, you're right to ask the further reflection and improvements. Let's evaluate the current solution and consider additional enhancements. On a scale from 0 to 10, I'd rate the current algorithm around a 7. Okay, maybe. It's a solid approach that addresses the X-trans pattern and uses green-guided interpolation, but there is definitely room for improvement. Areas for improvement. Edge detection and preservation. Yes, definitely need to do. False color suppression. Oh yeah, we didn't even touch this problem. Basically, what is false color suppression? It's when, let's imagine that we have this line, but it's not but like currently this line is, let's do like opacity. So here it's happening across green pixels. But if it will happen across different pixels, like this, for example, it will look like red, green, red, blue, green, red, blue. And this algorithm will generate huge number of like random colors. Somewhere it will be pinkish, somewhere it will be greenish, somewhere it will be yellowish. So it will be some colorful halo around this line. And this is called false color. So we definitely need to have false color suppression. Noise handling. Yeah, again, some very fine details will generate a lot of noise. We need somehow it suppress. moire reduction. Like X-trans sensor is famous to be almost not affected by moire. But okay, I can imagine some cases where it's still happening. Adaptive interpolation based on local image content. Yeah, this is what I was looking for, and I did not saw this. Like it was in second attempt, like with in this code, basically applied directional filter. It was like one attempt, and these matrices, it was like another attempt to amplify some features on the image, but it's not content aware at all. It's just predefined, and I would see more content aware handling. Okay, iterative refinement. I don't know what it means, honestly. Handling of saturated pixels. Yeah, saturation is another problem. Basically, when some pixels are blown out, like there was super light conditions, like when, I don't know, when you shoot landscape with sun in the frame, basically the sun will be oversaturated. And it might happen that some pixels, some channels will be oversaturated, like all bits will be 11111, basically like it will be 255 if it will be 1 byte, or 65535 if it will be 16-bit information. But some channels will happen to be not saturated, and this can cause like false colors, etc. So these cases should be handled separately, and this algorithm doesn't cover them at all. Okay, let's implement these improvements. I would like to see this. Set output, set interpolation green. Okay. I see that interpolation is changed. So gradient threshold. Okay, it gets, it tries to understand what kind of, oh, nice. Let me explain what's happening here. So for green channel, it does following. Very good approach. I like it very much. Basically, like if we want to, if we want to interpolate this pixel, what it does, it get values delta between these pixels and this, calculate basically a vertical gradient, horizontal gradient, width. Again, but it calculates gradient over 2 pixels only, which is not enough. So for this, I would do actually this, like gradient horizontal across these pixels, but it does only between this and this. And problem that here we don't have value. Oh, we probably can have no value. It depends how we will scan, how we'll interpolate. If this pixel will happen to be interpolated first, then we'll have this value. But effectively, these pixels will be always calculated or interpolated using vertical gradient. Because here we don't have value and here we don't have value. So effectively, these pixels, if we will like do like scan from left to right, these pixels will be always interpolated between these pixels. This pixel will be always interpolated effectively across this group of pixels, because this interpolated like between vertical, and it will be, okay, so either this or maybe this too, but like effectively like this and this. I don't like it. I would prefer to be able to interpolate across like this. So window 3x3 is suboptimal. in my opinion. Okay, then it's see basically difference between these gradients and so if delta is not large, it averages across all 4 values. If otherwise, it averages across vertical or horizontal one. Yeah, not bad, but suboptimal. Okay, interpolate red blue. Again, directions. It should somehow map. Okay, it calculates difference between green values. So it will use green as guidance. And average basically all numbers in this window. But what is the size of the window? Directions. Okay, 3 by 3 as directions. Again, very small window. Not optimal. From my experience, I would say that Fuji use window 6 by 6 to do this in their image sensors. 3 by 3 is not enough. Okay, refine colors. Okay, this is interesting because it will do something with probably false coloring. What it does, it scan image, then for every pixels it scans its neighbors, get output, get pixel. Yeah, so basically it's smooths out colors in 3 by 3 window. It adds current value with sum with average value and divides by 4, by basically calculate average between current value at current pixel and average color for all neighbors. Yeah, so it just smooth out color, and it's not great because for images where there are a lot of colorful details, like for example landscape where some green grass, some grass with flowers, and a lot of precise details like some thin lines, and these lines have some color information, and this color is different from neighbors. This will wash out these colors away. It will be mess. Demosaic. Okay, but I don't see suppress false. Okay, so suppress false color also. We just somehow missed this. What it does, it goes through the image. Average. It makes no sense because I don't see this average being used anywhere. Basically, why let's do some provocation, please. Add comments into function to explain every line and every variable. Basically, average here is not used at all. So it's a garbage code. It should be used somewhere here. Probably, I don't know, a red. I don't know what it so I feel that it should be somewhere in this formula, but I cannot do the guess out of my head. Calculates average, presents a natural color. But how it has been used? It's not used at all. Let's ask. Hey. You're absolutely right. question, and I appreciate your attention to detail. After reviewing the code, I realized that average variable is not actually used. Oh my gosh, and this is the state-of-the-art LLM. Amplification of the suppress false colors function. Oversight on my part, blah blah blah. Okay, hallucinate, makes sometimes happens, not a big deal. Let's try to understand. Let's revise the function to remove. Let's try to see how it actually works. So basically it's equivalent of 0.25 on G of green channel plus 75% of red channel. Okay, makes sense. So in this case, basically what it does, it mixes up 25% of green channel into red in hope that green channel has more correct information. And the same story for blue. While this, I think that it can work in some cases to some degree. But again, since it's not tied to any feature detection, I still would expect to see some artifacts. Okay, so that's basically it. So as you can see, it generates some code. It generates not bad ideas. I like many of these ideas. Actually, I tried to implement this code by myself some time ago, and during trials and errors, I came up to all of these ideas. Yeah, but I came up to much more ideas than LLM generates here, just because I tried, I saw the results, and I had this feedback loop. LLM doesn't have it. It just like construct all this code right out of the head. It's like writing on whiteboard. It's a very challenging task. If you will ask a normal human, like who never did this before, I would expect that human will fail. Human won't come up with all these ideas out of the box. So in terms of, is it better than average human? Probably yes. Is it AGI? No. Can it write normal code? Not yet. So it's still a tool. It still requires a lot of efforts from engineers to validate its output, to guide it, to correct it, to be able to come up with some results which you can actually use. So yeah, I will keep an eye on next versions of Claude, and I will hope that they will do much better job in coding in next revisions. So that's it. Thank you very much. My name is Alex, and see you next time. Bye bye.